Hello, everyone. I'm Jeff Bauer. I'm the EHT project scientist and chief scientist for Asia A, based here in Hilo. And today I want to talk to you about the Event Horizon Telescope and VLBI with the SMA. So this story begins with the picture that you see here, probably a picture that you have all seen one way or the other. And to us, it's a very exciting result. It's the first image of a black hole. It's the black hole in the galaxy M87. And this image is remarkable in many ways, but one of the most remarkable aspects of it is the scale. The diameter of that ring that you see is 42 micro arc seconds. And within that 42 micro arc seconds is contained a supermassive black hole with a mass of 6.5 billion solar masses. So today I'm going to tell you about how that image was made, what it means, and what some of the key technical challenges to doing VLBI at millimeter wavelengths are, and especially with a telescope like the SMA. And then where the EHT is going in the future, because this is really just the beginning of what we want to do in this field. So this image, of course, is the image that has launched 1,000 memes, one of my favorites, but there are many others, the cat's eyes, the eye of Sauron, and then the XKCD image or cartoon, which in typical fashion for XKCD is both entertaining and informative, right? That it projects that 42 micro arc seconds to a linear scale and shows you that it's about the size of the outer solar system. If you're like me, you might have experienced a bit of overwhelming response to all of these memes and this proliferation of this image, but we think it's worth it for the exciting science that's behind it. Now, I want to emphasize the many people who have contributed to this work, and you can see the EHT team here in Hilo in December 2019. This is back in the day when we met in person. And if you were coming to the SMA School in the past, you might have seen this very view here in Hilo. So this is about 120 people, about 1/3 of the EHT collaboration membership. It's a multinational, multi-continent collaboration with students, postdocs, engineers, astronomers, and technicians, many other people who've contributed. This is what our collaboration meetings look like now, but we are still going strong and working together, and you can see everyone here. I do really want to emphasize the really important contributions that have been made by early career researchers, and we recognize a number of them here who made really outstanding contributions to the production of this image and the science that went along with it. But this is also it's also a very technological activity and a very hands-on observational activity, and you can see the many teams that we sent out to telescopes around the world to carry out these observations. You see in the lower left the SMA, some of the SMA staff who participated in that. You see other facilities, ALMA, the Pico Veleta, the LMT in Mexico, the South Pole Telescope, the SMT in Arizona. Finally, in one more slide here, giving credit to those who've contributed. So here are some of the local people here in Hilo who have made contributions. Again, astronomers, engineers, technicians, and a real wide gamut of people who made this happen. So the story starts here. This is a radio image of the center of the galaxy made with a Meerkat telescope. And the Sagittarius A star, the supermassive black hole in our galaxy, lives in this saturated region at the center of the image where my cursor is here. And of course, the Sagittarius A star is very famous. That in the last year, Reinhard Genzel and Andrea Ghez won the Nobel Prize for their amazing observations of stellar orbits around Sagittarius A star, confirming the existence of a black hole, measuring its mass and its distance with exceptional precision, and detecting a number of general relativistic effects. So Sagittarius A star definitely constitutes our best case for the existence of a black hole. EHT actually has two main targets, Sagittarius A star and M87, which by the virtue of a kind of a cosmic coincidence have the same angular diameter on the sky of around 40 to 50 microarc seconds. That diameter, or the shadow, is just the ratio of the gravitational radius, or 10 times the gravitational radius, divided by the distance. M87 is 1,000 times more massive than Sag A star, and about 1,000 times more distant, which produces the this coincidence in diameter. Now, M87 is an unusual and an interesting source. It was first noticed to have a jet in the optical over a century ago. That, of course, was not well understood at the time. This is an HST image of that optical jet. M87 itself is an elliptical galaxy at the center of the Virgo galaxy cluster. If you look at it at radio wavelengths, you see this beautiful jet, and which goes down to on all scales. And in this bright, compact region at the base of the jet is where that black hole ring image, shadow image, is present. Now, what is that ring? What is it that we're seeing? Well, what we're seeing there is a ring that is shaped by the gravity of the black hole itself. The light is bent by the mass of the black hole and comes out at an impact parameter, which is fairly insensitive to most aspects of the astrophysics and the black hole physics of about 10 times the gravitational radius. And this was first predicted in detail by Luminet, and this is a hand-drawn simulation of what he predicted for a view of a black hole. And at the time, he didn't think it was at all possible that anyone would be able to image this. Now, over the decades, we've developed more and more sophisticated simulations, and this is one example that shows accretion. But no matter how much physics we add to it, to the accretion, our understanding of the accretion flow, presence of a jet or not, we still come with the same kind of prediction of a ring-like feature, very narrowly defined. But this is what VLBI data on M87 actually looks like. This is from a decade ago now, a 3-element experiment using the JCMT on Mauna Kea, the SMT in Arizona, and the Karma telescope in California. And we obtained visibility amplitudes as a function of baseline length, not enough to make an image, but thinking back to your understanding of the relationship between visibilities and images, right? We can model these visibility amplitudes as the as a Gaussian source on the sky, and in this case, a Gaussian source of about 40 micro arc seconds. But we certainly could not make an image from this data and discriminate between different kinds of models. So why is it so hard to make this kind of image? So for one, we need this ultra high angular resolution in order to be able to resolve it. So that's short wavelengths, extremely long baselines. There's no existing dedicated array that can do this. The atmosphere is a limitation. Only the highest and driest places will do. And so the SMA located here on the summit of Mauna Kea, and these other locations around the world are necessary. And then finally, we're starved for sensitivity. SMA is sensitive. The ALMA is really sensitive, but nevertheless, the sources are not that bright, and we need a lot of sensitivity. And we also make use of really high data rate recording at 64 gigabits per second at each telescope in order to have the most bandwidth and instantaneous bandwidth to come over atmospheric phase fluctuations. So as I said, ALMA, very important to this measurement. And both ALMA and the SMA, as you know, are interferometers themselves, just like the EHT is an interferometer. And a key technical development for the EHT is to phase together the elements of the array. That is, to add them coherently. So as you add more antennas together, you get more signal. And this was something developed with the Casper digital technology tools, and the team at CFA, led by Jonathan Weintraub, was instrumental in implementing this. And this is just an example of showing what happens when you introduce the phase corrections in real time that allow you to sum together the signals and build a more sensitive telescope. You essentially go from no sensitivity to full sensitivity. The other really challenging part of EHT imaging is maintaining an accurate clock. This is a multi-step thing. We use GPS to give a very stable long-term time reference. And we use a hydrogen maser coupled with a local crystal to provide very accurate short-term time stability on time scales less than 1,000 seconds. And so there's a well-shielded hydrogen maser living underneath the SMA control room in a concrete bunker. It requires great stability in temperature and other environmental factors to produce this stable result. Okay, so I've already introduced many of these telescopes already that contributed to this image. Again, going back, and this is the visibility amplitudes that we obtained for M87 from the 2017 data. And you can see already that it's much richer than what we had previously. And we're able to immediately infer ring-like structure from this data. This dashed line here is a Bessel function model for a ring with a diameter of about 45 microarc seconds. There's some asymmetry that's clearly included here because where we have a null in the Bessel function, we also have some points, visibility points, which are not in the null. And that says that some baselines are sensitive to the asymmetry or to an asymmetry, and some are not. And also we see that large scale structure is resolved. The short baselines that we measure don't add up to the full zero spacing flux of the source. And that means that the jet itself is partially resolved out. So this is a neat little video of how Earth rotation synthesis works that shows building up the image as the number of baselines build up as we fill in the visibility plane, fill in this visibility amplitude space, and get a more and more complete imaging picture. One of the things that I'm very proud of in the production of this image is that it is probably the most thoroughly vetted image ever made in radio astronomy, interferometric image. Multiple imaging techniques, multiple days, all show really great consistency over time and over the techniques in this basic image. So what have we done since then? Well, one of the major results we've had is going back to some of this earlier data and not imaging it because it still has a limited set of baselines available, but modeling it using this same disk-like model that we used to model the 2017 image. And this has a great result showing that all of the data is consistent with a ring structure of similar diameter. But interestingly, with potentially rotation of the asymmetry. So the similar diameter is the most important part of this because it really says this is not an artifact, this is not a feature, this is not some weird optical illusion that we've caught. It really is a stable feature of the system, and that supports the gravitational lensing interpretation. Now, M87 is not the only target that we've published results on. We see a really fascinating structure in the blazar 3C279. In fact, where it looks like we're able to measure motions within the system over a time scale of just a week in observations, and there's a bend in those motions. We think that's probably best interpreted in this kind of helical corkscrewing of the jet material that's shown in this simulation here. We're also hard at work on polarimetric imaging of the black hole magnetosphere. And we're looking at synchrotron emission that comes from the vicinity of the black hole. Synchrotron emission is linearly polarized, and that the orientation of that is partly determined by the magnetic field orientation and also by Faraday rotation effects. And the combination of understanding that can give us clues to the nature of the accretion flow in the jet on these very small scales, and potentially allow us to discriminate between different models. So everyone always asks, what's the story with Sagittarius star? Well, this is where we were a decade ago, not very different from M87. Very limited set of measurements and very limited constraints. The best image that we have so far, this comes not from EHT data, but 3mm wavelength VLBI data. And it's a fuzzy blob. That fuzziness comes from angular broadening due to interstellar scattering along the line of sight of radio waves as they propagate from the galactic center through the galactic plane and interact with plasma along the line of sight. And that's been seen. It has this characteristic lambda squared profile to it. And one of the reasons that we go to the very shortest wavelengths, go down to a wavelength of 1 millimeter, is because at that scale, the intrinsic structure of the source will dominate over the angular broadening. So that's what we're at work on. One of the big challenges, in addition to the scattering, is that Sagittarius A star is highly variable. On a time scale of hours, we see significant variations. And that means that when we use synthesis imaging, we're over the course of 8 hours, we're violating our own assumptions about how VLBI works. That the source structure may be changing on that time scale. It's all coming together. Our team is working very hard on it. You can expect to see results soon. Okay, so finally, let me wrap up here. The future of the EHT is very bright. As I mentioned, Sag A star is coming soon. Polarimetry of jets and accretion flows is coming soon. And we have a whole host of other data sets on active galactic nuclei, of pulsars in the galactic center, multi-wavelength data. In the more distant future, we're looking at making movies of these systems. We want to achieve higher image fidelity, see the connection between the accretion flow and the jet. And we want to look at more sources. So the SMA is a really critical part of this experiment and has been throughout its history. This is a great opportunity for you as students in this SMA school to learn a bit about VLBI. Thank you.